So I'm going to tell you about NASA's Chandra X-ray Observatory, which is one of NASA's great observatories. And the picture I'm showing here is an image that was minted to celebrate its 20th anniversary in 2019. But I should emphasize that the satellite won't look like this now because it's been in space for a long time and we know its thermal insulation is degrading, etc. So we see the temperature going up. So I'm going to be using these arrows. I've now discovered how to forward my slides. So what I'm showing here is NASA's great observatories. There are 4 of them. And in order to understand what celestial sources are like, to be able to get a full picture, we need to look in multiple wavebands. So the great observatories are designed to cover quite a wide range of wavelengths. The first one to be launched was Hubble Space Telescope, which I'm sure everyone has heard of. It seems to be much more famous than the others. I actually always put it down to the fact that they figured the mirror wrong, and we had to send up shuttles to fix it, put glasses on it, and so we had to sell it to the public and the government to get money to do that. But of course, its pictures are amazing, and science is amazing, and we do a lot of work with them as well. So Hubble looks in the optical UV light. So I'm showing at the bottom a wavelength scale going from short wavelengths in the gamma rays on the left through to the radio wavelengths on the right. We still do radio observing completely from the ground. And so Hubble is a visible light part of the spectrum, plus it goes into the UV somewhat and a little bit into the infrared. So this is the light we see with our eyes. The next one to be launched was CGRO, the Compton Gamma Ray Observatory. It looks at very, very high energy gamma rays. And that is actually no longer operating. It came down from its orbit and landed in the South China Sea quite a while ago now. But another one was launched not long after that called the Fermi Gamma Ray Telescope. It's an Explorer mission, and it's doing a great job of observing in the gamma rays. So it's become the next great observatory in the gamma rays. Then we launched in 1999, looking in the X-ray. So we've got gamma ray at the very left. We've got the X-ray here in the blue and the purple, and then the optical. And then a few years after Chandra was launched, the Spitzer Space Telescope was launched and observes in the infrared. Sorry, I must have hit the wrong button. Observes in the infrared. So like the cool coals on our barbecue. So by looking in all these telescopes, sometimes we actually look with all of them to get a complete picture of a source. The temperature gauge above the wavelength scale shows you the temperature that material or plasma or gas and dust has to be at to emit in that waveband. So visible light, with the temperatures that we're used to seeing. If you have your barbecue coals and you've just lit them, they'll be red, and when they're white hot, they're hot enough to cook on. So they're hot at the temperature, the bluer the light. And so to get into the X-rays, they're extremely hot, a lot hotter than your barbecue grill. Okay, so Chandra was launched on the Shuttle Columbia. And this is just a movie of the launch. This was in the middle of the night on the 23rd of July, 1999. And it was actually the 3rd attempt when it finally went up on Columbia. Columbia was the only shuttle that could actually fit Chandra into its cargo bay. It's the biggest thing that has ever been launched by any shuttle, biggest and heaviest. And has any of you ever been to a launch, actually physically been to a launch? Because it's a really amazing experience. If you ever get a chance, I recommend it. We were down at launch. My kids were little at the time, I think about 6 and 4, and they stayed awake for this. Or at least my son was woken up for it. He was asleep at that point. But the sky is completely light like day for quite a few seconds, probably 20, 30 seconds. And the ground under your feet actually shakes. So it's actually quite a moving experience to be there. And we were 2 or 3 miles away and still the ground was shaking. It gives you an understanding in some way of how much power it takes to escape Earth's gravity, which is what you're doing when you launch a satellite. And it's also sort of amazing to realize that the human race can do that, put that much power into something, actually launch something and escape from the Earth's gravity. So I definitely recommend it if you ever get the chance. It's the only one I've ever seen. I haven't seen another one yet, maybe one day. So the first thing the crew did when they actually got up was to let Chandra go, because it's also full of its own fuel, and you'll see why in a minute. We didn't stay in the orbit that the shuttle put us in, which is where Hubble is. Hubble is in a 1.5 hour orbit around the Earth. So they let Chandra go and then backed away very, very slowly and carefully. And this is a movie taken by Katie Coleman, who was a mission specialist for Chandra, and she's sort of hanging at the window looking out at Chandra, and so you can see it's moving around a bit because she's basically floating. There's no gravity up there, and they just backed away quietly so that if anything had gone wrong with all the fuel on board, it would have blown up the shuttle as well. So it was the first thing they do, and actually when they first get up there, they usually have a rest. So this is quite a difficult mission for them. I also should have said that a couple of things. The commander of the satellite was Eileen Collins. Of the shuttle was Eileen Collins. She was the first female commander of a shuttle. She's quite a character. We've actually met her. They take quite an interest in Chandra. I think often when they go up to space, they do a few experiments on the shuttle, and I'm sure it's an incredible experience, but they don't often put up a big satellite that's still working and producing images 23 years later. So they're part of our family, and we're part of theirs, which is rather nice. Another interesting thing that happened was that one of the engines on the shuttle had a little bit of a fuel leak. So Chandra, the whole shuttle didn't actually end up in quite the orbit we were expecting. It was a few miles too low. And so the aerospace engineers who were taking Chandra through the launch and into its final orbit, they were from TRW, now called NGST. They were back in Cambridge, Massachusetts, which is where the control center is, and they had to completely recalculate all the firings of all of the engine to get to our final orbit, because they were starting from a different place. So it's what they do. I guess they're professionals. It wasn't too difficult, but they had to start from the beginning again. But we did end up in the final orbit. And this is a schematic of the orbit. It's a 3-day orbit around the Earth, 63.5 hours. It stayed pretty much the same over 23 years. It started in this green initial shuttle orbit on the left here, small orbit. And as I said, that's roughly where Hubble is, and Hubble stayed there. And then they fire at the perigee and the apogee, one after another, to raise, mostly the apogee, to raise it into this final orbit, which, as I say, is 3 days. And in the next slide, we'll see how that compares to the orbit of the moon. Excuse me, it goes to about a third of the way to the moon. So on the right here, we've got the moon's orbit, just cut off a bit. It's a fairly circular orbit around the Earth. And here's the Earth with its, in red, the radiation belts around the Earth. And this is Chandra's orbit. So it goes about a third of the way. It takes 3 days to do this. And then zooming in on the orbit itself on the left, you can see that it spends quite a bit of space anyway in the radiation zone. It's actually only a small proportion of the orbit in time, because it goes much more quickly when it's close to the Earth. But we do shut down the instruments and stop observing for about 16 or 17 hours while we go through the radiation zone, because otherwise we would hurt the detectors. Okay, so that's where we're seated. So how do we focus X-rays? It's not at all the same as focusing optical light. So at the top here, we have what happens with a visible light mirror or a telescope. You could also, of course, focus it with a lens rather than a mirror. But the light comes in when it's coming from a celestial source. It comes in parallel. So these are parallel rays of light shown in blue. They hit the mirror here and come back to a focus point where you would put your detector for a ground-based telescope, for example, or a space-based optical telescope. But if you put X-rays into that mirror, it won't even see the mirror, they'll go straight through. As we know, X-rays really penetrate. The doctors use X-rays to take an X-ray of your broken arm because you can actually see through the skin and see where the bone is broken. So how do we focus them? Well, we do so with grazing incidence. So that's what I'm showing below here, the incoming X-rays coming in parallel. And this is a cross-section of actually a cylinder, and I'll show it to you in a minute. So we actually collect a circle of light, of X-ray light. And it comes in at between 1 and 3 degrees, depending on the energy of the light of the X-rays. And it gets reflected, grazing incidence of 2 different mirrors. One's a hyperboloid and the other's a paraboloid in shape, and comes to a focus at a point which actually for Chandra is 10 meters away. It's the size of a school bus, an American school bus that you see in the movies. So that's how we focus the X-rays. And this is showing the light path through Chandra. So this is a schematic of Chandra with the light rays coming in orange, coming in from the left. The mirrors are right here. The first thing that the light hits, the X-rays hit, and then they get focused down 10 meters away to the detectors on the far end. And then I have a cutaway which shows what the mirrors really look like. This is backwards. The X-ray light is now coming in from the right-hand side. And we have 4 what we call nested mirrors. So they look like cylinders. The first one is a paraboloid, the first 4, and they're inside one another. And the second 4 are hyperboloids. And so these doubly reflected X-rays, as I mentioned, go down to the detectors 10 meters away. So that's how we focus X-rays. Very different technology. The mirror area has to be a lot bigger compared with the amount of reflections we get off it. And also it has to be a much smoother surface because the X-rays are coming at a small angle. They'll see every kind of blemish or anything wrong with the shape of the mirror very easily. Just like when you're lying on the grass and you look at the grass lying sort of along the grass, you see all the grass blades of grass, whereas if you look down from above, it looks like a green carpet, right? So here we're looking at the blades of grass, and if any of them stick up, the X-ray will go off at the wrong angle. So this was the smoothest mirror that's ever been made. It's about 70 times smoother than that on the Hubble Space Telescope, for example. And Chandra was the first X-ray telescope to have resolution that's comparable with a ground-based optical telescope. The resolution is about ½ an arcsecond. And that's what you can get with a ground-based telescope on a really good seeing at night, unless you have some kind of active optics. Okay, so now I'm going to start talking about what we see with Chandra. This is a picture in the X-rays of the Orion Nebula. The Orion Nebula is a star-forming region. You can actually see it with the naked eye. Some of you may have done this. It's in the middle of Orion's dagger. And if you look slightly away, you'll see that the middle of those 3 stars is actually not a star, it's a little fuzzy blob, and it's the Orion Nebula. This is a place where stars are forming. So there's a lot of gas and dust in there, and then young stars, the gravity is pulling the material in and forming those stars. This picture was taken with the previously best highest resolution X-ray mission called ROSAT in the early 90s, I think was when it was launched, and working for 2 or 3 years. In this image here, we see 250 sources. And if you look at the center, there are so many stars there that they all blur together. It's what we call confusion limited. You can't separate the stars from one another, except for the brightest one. So you've got these 3 very bright stars, for example, in the middle. Now, when we looked at this with Chandra, this is what we saw. Now we have 1,400 sources. We can still see the 3 bright stars, and they look big because the point spread function is very narrow, but you get light when you've got a bright source all the way out into the wings of the point spread function. However, if you look carefully, you can see little stars here in the wings. So we're seeing pretty much every star that has an X-ray source here, and there are 1,400 of them. Young stars are very unstable in violent places. Gravity is pulling material in, it gets in its way. One bit of cloud of material gets in the way of another, they get hot. It's like if you rub your hands together, they get hot. Some of it gets blown out, and so you get jets coming out of the poles, and you get material falling in. A very, very hot place. So they're bright X-ray sources, all of them. And the advantage of the X-rays is because we can see through all that gas and dust that is forming the stars, we see all of them in the X-rays. Whereas in the optical or infrared, you wouldn't be able to see them all. So if I add an optical picture here, so we're seeing now lots of gas and dust. Some of it's bright, some of it's dark, so it's cool and it's not emitting. But we still see all these young stars that are blue. We see them all in the X-rays, even the ones on the back of the cloud that you can't see with the optical. So it's a really good way to find young stars, and we put the X-ray data together with the optical data and learn a lot more about how these stars are formed in star-forming regions. Okay, so where do the X-rays come from, apart from young stars that we've just looked at? They come from the hottest and most violent places in the universe, and I might argue the most exciting, of course, not that I'm at all biased. And so here's a list of them here. We've just talked about stars being born. When stars interact, we also get very hot and violent places, so a lot of X-rays. When they merge, and also when they die. Black holes of any kind, it's accreting material, so the gravity from a black hole tends to pull in, suck in everything around it. And so when it's doing that, that material gets very hot and you get X-rays from them. And this is any size of black hole, from a stellar mass black hole to a supermassive black hole. When they're accreting, they're very bright X-ray sources. But even galaxies like the Milky Way, they have a lot of hot gas that we can only see in the X-rays. And I'll show you some of that. So in order to understand a galaxy, which has a lot of stars in it, obviously, to see everything, we actually have to look in the X-rays as well. But even planets, we see X-rays from planets. Usually they're as a result of the solar wind interacting with neutral particles in their atmosphere. But in Jupiter, for example, this is a picture taken by the Juno satellite, which is actually going around Jupiter right now and taking pictures. So these are beautiful pictures in the optical. And then purple is shown the X-ray aurorae on the two poles of Jupiter. And these are thought to be due to Jupiter has a high magnetic field, and it has a sort of disk of material at the equator, so an equatorial ring of plasma. And that gets pulled up by the magnetic field towards the North and South Pole and creates these X-ray aurorae. So the magnetosphere and the plasma. So basically, most types of celestial sources do give us X-rays at some point during their lives. Why do we need so many telescopes? I've said this a number of times. Here's a really good illustration of why. This is a picture of Centaurus A, which is a radio-loud active galaxy. Active galaxy means we have a supermassive black hole in the middle and it's sucking in material, so it's very bright. It's an active nucleus in the galaxy. Radio-loud means it's emitting radio emission. So if we look on the right first, in the middle is the classic, what we call double lobe radio source. We have a supermassive black hole that just sends jets out in two directions, in the polar directions, and this is plasma, electrons that are basically caught by the magnetic field. They rotate around the magnetic field and they end up interacting with the medium around and slowing down and creating these lobes in two directions. So this is the radio emission from that source, and it's a very bright radio source. In the optical, it looks like an elliptical galaxy, a fairly amorphous, smooth, elliptical kind of shape, but it's an unusual one in that it has this dust lane there through the middle. So actually, it's quite hard to see down into the middle of this source in the optical. And then the top picture here is color-coded X-rays. We color-code them using a rainbow, like we do in the optical. So it's not really rainbow light, it's X-ray. But red is the lower energy X-rays, and the white and the blue is the higher energy X-rays.
And so this X-ray picture is really complicated. It has a lot of different components with different energy X-rays. The red is mostly coming from the elliptical shape of the galaxy. The white hot is coming from the jet. And we also see quite hot emission around where the dust disk is. So we put it all together and add the star field around it. This is what it looks like. And it's only when we put all these together that we see all the different components. So that's why we need to look at sources in different wavebands. And another analogy we use, if you have an elephant and all you see is its tail, you would have no clue what that elephant looked like. You really have to look at all parts of it to see the trunk and see the huge structure of the elephant. So we're seeing the whole elephant in this source. So I'm now going to look at supernova remnants. When a massive star, much more massive than our sun, runs out of fuel for fusion, fusion is the power source in the center of a star, it explodes. And in the next slide, I'll show you a schematic of what happens. So on the left here, we have what's called a red giant star. So this is a star that's running out of fuel. It's a very massive one, and it tends to expand out and become a red giant. Red in color, and giant means big. We just use straightforward English words in astronomy under this medical Latin terminology. So it runs out of fuel, and what that means is that the gravity can now win. The star, when it's in equilibrium, has gravity pulling the matter together and holding it together, and radiation coming out from the center, which balances that, works against the gravity. So you have an equilibrium, and that's where our sun is at the moment. But if you suddenly lose that radiation, then gravity wins, and the center of the core of the star collapses and actually makes a neutron star. So you get very, very dense material in the core. But the reaction to that further out in the star is that you get the outer parts being blown out. So it explodes outwards and makes a supernova. A supernova shines as brightly as the galaxy itself for a few hours to days. So that's as bright as 100 billion stars that are in the galaxy. So very, very bright. And then as it cools off, it fades, but this material keeps moving out, and this is called the supernova remnant. So it's all the outer parts of the material of the star that just keep moving outwards as time goes by. And our official first light picture was the supernova remnant Cassiopeia A. We knew this was going to look pretty nice because we'd seen it with ROSAT, but with a much worse resolution. So we thought it would make a good first light picture to give to the newspapers that show that Chandra is working. So this was the first light picture. In this image, we found the stellar remnant, which is a neutron star in the center, which had not been seen before. This source is about 29 light years across, and it's 340 years old. So it's pretty young for a supernova. And most of the material, because it's young, is still very, very hot. We then looked at it for longer. So you can see some structure here now. It's mostly spherical, but there's a jet, for example, coming out here. When we add more signal, look at it for longer, this is what we see. All that structure sharpens up, and we can see very complicated structures in there. And the colors actually tell us something about where the elements are, and I'll show you that in a minute. This was actually a 12 days worth of observations. They weren't taken in 12 days that were consecutive, but the data were all added together. But 12 days worth of observations to get this picture. So then this is the same slide on the left. I should also say that the colors in this image are according to the energy of the X-rays. So the red are the low energy, and the blue are the high energy. Green is in the middle. On the right, I'm showing you the optical picture of the supernova remnant. So you still see the structure of it. You see a lot of stars. These are not stars that are in the supernova remnant. They're either in front of it or behind it. So that the star field, we would call it. But there isn't anywhere near as much structure in the optical because there isn't as much material there that's cool enough to emit in the optical. However,
by observing the optical as well, we can get a better handle on the physical conditions of the material. It's where there is cooler material, then we can measure the temperatures to be cooler. So again, combinations of different observations are really powerful. What do we do with the neutrons, with the supernova remnant? We find the neutron star, and we've done that in a number of supernova remnants now, and we study it. We also can look at how the star blew up. So if we look here, you can become observers for a minute. I'm going to go to the next slide here. Whoops, not that one. Okay, on the right now, I'm showing the spectrum. Actually, in X-ray detectors, for every photon that comes in, we get not only a position, which gives you the image, but you also get the energy of that photon and actually the time it came in at as well. So you can do spectroscopy at low resolution and also timing studies, which are not particularly useful in supernova remnants, but the spectrum is. So here I'm showing the spectrum. The shape of this in terms of continuum gives you the response of the instrument. But you see these emission lines here coming from different elements, so silicon, sulfur, argon, calcium. So by looking at these colors over here, the same color coding, we can see that this jet, for example, is primarily made of silicon. And I want you to notice that there's a big iron feature here. Iron is in the core of the star. That's the last thing you make, and you can't use after that. So the core of the star should have iron. And where is the iron in this remnant? It's all on the outer edge here. So the star somehow blew inside out. And just hit the wrong button again. And the iron, some of the iron, of course, is still in the neutron star, but some of it got blown out and actually went faster than the other material is out on the outer side. The blue, which you could put your hand up and say, but Belinda, there's blue that's further out. That's true. But this blue emission is non-thermal emission. It's like the jets that I talked about in Centaurus A, that you've got plasma, electrons and protons spiraling around magnetic fields, making synchrotron radiation. We call it non-thermal because it's not shining because it's hot, it's shining because the electrons are there with a lot of energy. So that is a component that we'd seen in the radio before, but not in the X-ray. So here we're seeing it. We can also, and we got a sneak preview of this, see it expand. So over time, this is a little movie of observations going up from 2000 to 2013. And if you look carefully, you can see this expansion happening, and also the structure changes further in, but that's coming towards us, and the filaments just move. It's not very often we see something changed on a time scale of a few years in astronomy, except when something blows up, of course. So this we've been able to watch. That also means we can't make a more high signal to noise image of this source, again, because the motion is going to blur the structure. This is another supernova that we've been monitoring every 6 months since the beginning of the Chandra mission. It's called supernova 1987A. It's very, very young. It went off in 1987, strangely. And so here are images starting in 1999 and going to 2015. And as you can see, it gets brighter the whole time. It's a ring of emission. It just gets brighter and brighter. And that's because before the star blows up, it releases some material because it's beginning to die. And you get this circumstellar ring of material. And as the shock wave from the supernova remnant moves out through that material, it heats it up, and you start seeing X-rays from it. And we've actually started seeing now that it's fading on certain sides. So we've got to the end of that ring of material. So we also can find out how much material there is. And that started happening after about 10,000 days. We haven't yet seen the progenitor. We haven't seen the neutron star. There's too much material in the center to be able to see that. Hopefully we'll see it before Chandra dies. At the moment it's still working very well. Hopefully we'll be able to see that, but not yet. And here's another supernova remnant, actually. It's called a pulsar wind nebula. It's the Crab Nebula. It also has a movie, which doesn't seem to be doing. There we go. This is in the X-rays in blue, and the data from Hubble is in red and yellow, and optical. So the Crab pulsar is very famous. It was the first one that was found. It was called Little Green Man 1 because man in his wisdom, I should say human race in their wisdom, couldn't believe that anything out there could pulse milliseconds so accurately. Had to have been made by humans, right? But oh no, or some other species that would be cleverer than humans. But anyway, so this is the crab pulsar. It's a bright X-ray source. It has a high magnetic field, and it has plasma around it that is ionized, and we're getting synchrotron radiation from here as well. And as time, this is about 7 observations taking a month apart. We see this jet, we see the structure change a little bit. There are standing waves that plasma moves through and gets bright as it moves through. Looks like a spinning top, it's not actually spinning. And we also see it in the optical, but there's also a lot more cool material around, which sort of makes it harder to see. So these are there's jet in this direction, so bipolar jets here. Okay, so that is actually also the result of a supernova. And here are some more. This one here we also have seen expand. Looks very like, it's very spherical, like Cassiopeia A. This one is 2. This looks completely different. Obviously, it has blown up more in the horizontal than in perpendicular way. It also has a pulsar with nebula in its core. So they're all different. They're all interesting, and they're all beautiful. So we use them a lot for press images. Okay, I'm going to jump a lot further away now and look at quasars, which are galaxies that have a supermassive black hole in the core, like Centaurus A that I showed you at the beginning with that multi-wavelength picture. So this is a radio loud quasar, and this is the radio image on the right. A very bright spot is the supermassive black hole with all its hot material around it. There are jets coming out from that in a horizontal direction. There are hot spots where those jets impinge upon material around the jet, and it slows it down, and some of it flows backwards, and you get these 2 lobes. Classic double radio source. This is a really beautiful one. It's very powerful, and it's the most nearby powerful supermassive black hole. On the left is a schematic of what we think is happening right down in the core. So we have the supermassive black hole is right down there. We can't see it. Obviously, it would be black. You wouldn't see it anyway. The material around it makes a very bright spot. There are jets coming out, up and down, sort of north and south, if you like. And then around it, there's material which is in a accretion disk that's very bright in the center. And then as you move away, there's cooler material because it can't see, that cool material can't see all the way down into the center. So when you have it almost edge on like this, it's actually quite hard to see the supermassive black hole in the center. That's not how Cygnus A looks. We're looking face on because it's pretty bright. Okay, so this is a quasar. And I want to tell you another story here. The first targeted source, so before we looked at Cassiopeia A, we had to make sure our telescope was focused. Well, we had to focus it, in fact. And so we looked at a quasar, because when you put a quasar a long way away, all you're seeing is that accretion disk around the supermassive black hole. Is a point source. So any of you who have a telescope know that you need a point source to focus your telescope. A star is also a point source, but they're not bright in X-ray. It's not bright enough to focus this. So this one is 9 gigalight years away. It's at a redshift of 0.66, if that means anything to any of you. And so here we are. We looked at it. What did we see? We saw a point source. This is a point source where you're actually seeing right into the wings of the PSF, but it is a point source. We could focus the telescope. But on the west side here, we have this extension, this fairly linear extension. And we didn't know what that was. We weren't expecting it. So the people in the control room, this is the first thing we looked at, were a bit concerned there was something had gone wrong. Maybe one of the mirrors was misaligned, or something was in the light path and the X-rays were going off to a weird angle. But they couldn't figure out how you get that structure so linear, just in one direction. And then someone else in the control room, I wasn't there, but a colleague of mine who, along with me, had worked on this source said, hey, this is a radio loud source. It's got a radio jet, just like Centaurus A does. Where is the radio jet? And they looked it up, and it's on the west side. So what we discovered by just focusing the telescope was X-rays coming from a radio jet. Radio jets have been known for 40 or 50 years, but we hadn't seen them. except in one very odd case, in any other wavelength. This is very long. It's 9 arcseconds long. It's 250,000 light years at this distance, so very long. And I'm just going to show you a zoom in on the X-ray jet in the top here, showing these are contours of brightness, which are also color-coded. So the quasar on the left, the jet extending to the west with a brighter spot here. And then below we have the radio jet, which is high resolution because they use interferometric telescopes to make a bigger dish. And you see this structure of the jet is lying right on top where the X-rays are. So X-rays from a radio jet. The radio jet bends at some point. I've got it marked as jet bend, and it must be coming up against some heavy, cold, dense material that's curving the magnetic field in those plasma that's moving around the magnetic field lines. It must bend it. We don't see any X-rays from here, and we think that's because the plasma is no longer has the energy. These electrons don't have the energy to produce X-rays, but they can still produce the low energy of radio. But we think that this X-ray is due to synchrotron emission also, so from very high energy electrons at this place until we get to the bend. Okay, so this was the discovery and the beginning of multi-wavelength studies of jets that have been, and as a result, we understand jets much better than we used to. Here's another one. It's called Messier 87 or M87. It has a quasar in its core, but it's very nearby, and it's sitting in a cluster of galaxies. And what we're looking at right now in this orange is the X-rays from the cluster. There's a lot of hot gas in clusters, and we'll come back to this. But if we look carefully in the core here, there's also a jet in the X-rays. So here's the jet, the X-ray jet. Bright spot here coming from the supermassive black hole, extending to the right-hand side with a hot spot, a couple of hot spots there. And if we zoom in further and put them horizontally, on the top here we have that we have a radio jet. The bottom we have the X-ray jet we were just looking at. And then in the middle we actually see this jet in the optical with Hubble as well, which has the highest resolution. And so what I want you to look at is the supermassive black hole is on the left in all these pictures. This is on the same scale, but you can see that the brighter spots, what we call hot spots along the jet, are reproduced from the radio to the optical and to the X-ray. So we can study these hot spots in multiple wavelengths and constrain the physical conditions in those individual hot spots along the jet. So these are the reasons why we know much more about jets than we did before. It's these multi-wavelength observations. I can also not resist telling you that if we zoom in on the core, this is the source for which we saw the first image of the shadow of a black hole. So with the Event Horizon Telescope a few years ago, and we've now got a similar picture for the supermassive black hole in the Milky Way, also from the Event Horizon Telescope. This is actually 40 micro arcseconds across, which at that redshift is 4 light days. It's 50,000 times below the resolution of Chandra. So in the radio, they had these radio telescopes all across the Earth. So they are synthesizing a very large dish and could get extremely high resolution. We looked at this source simultaneously with the EHT, the Event Horizon Telescope, with Chandra. And so we were able to see some of the X-rays are coming from right down there. We can't see that they're coming from right down there, but we see them and we see the variations. And so we were able to constrain some of their models because they had to make sure they didn't exceed they had to get the X-rays right as well, right? So it was really fun to be part of that with Chandra. Okay, we also have binary supermassive black holes. They like to come, if they get too close to one another, they get caught and they become a binary supermassive black hole, very like a binary star, but much bigger. And Chandra's been able to find quite a few of these because in order to be sure you've got an active nucleus or a quasar, which is what we've been talking about with a supermassive black hole accreting material, you need to see it in the X-rays to be sure that's what you have. So here's a couple of galaxies in the red that are merging together. They're actually spirals, but their spiral arms are going in all weird directions. because they've got too close to one another and they can't escape. And so it's now a mess. They will eventually merge. And with Chandra, we found that the two hotspots that had been seen in the optical are in fact both active galaxies, both quasars. In this source, they're 300 light years apart. That's a lot smaller than a galaxy, about a tenth the size of the galaxy, and they will merge in about 100 million years. And then these pictures, I should say, are thanks to our education outreach team on Chandra, and they made this movie of what is happening in NGC 6240. So we have two spiral galaxies coming together, they capture one another, and then if we zoom in the middle, they're now showing little disks of accretion disks with a black hole in the center, if you look carefully. They're moving around each other, and eventually they will merge because they'll slow down, they slow each other down. And when they merge, we'll see gravitational waves, which will be shown in blue. We won't see those from the Earth on LIGO. We'll need a space-based gravitational wave detector such as LISA. When it's up, we'll be able to see gravitational waves at these frequencies. We've seen more of these double sources. There's a couple more examples. In the left, the ground-based Magellan telescope in yellow, and the two AGN in the middle in blue. And on the right, the opticals in red from the Sloan Digital Sky Survey, and then the X-ray picture. And then finally, we've seen a triple. So this is the optical picture of the triple in white and orange on the right side. And these black holes are separated by about 30,000 light years. And in the X-ray, we see all three of them. So we know they're all active galaxies. And these will actually merge more quickly because there are now three of them interacting with one another. We won't see it in our lifetime there. Okay, so now I'm going to move to the largest gravitationally bound structures in the universe, clusters of galaxies. Just like stars tend to come together in clusters, galaxies tend to come together in clusters as well. And clusters of galaxies can have anywhere from 50 to 1,000 galaxies that are bound together by their gravity. They can't escape from the system. And there's a lot of hot gas in clusters. Here I'm showing the center of the Perseus cluster, which is quite near us, in the optical. And this, the biggest galaxy, this sort of spidery red thing here, is NGC 1275. It has all these filaments of star formation. And now I'm merging from the optical picture into the X-ray picture. And you can see all the X-ray gas shown in orange is filling all the space around those galaxies. And there's actually 10 times as much material, X-ray emitting hot gas that cannot be seen at any other wavelength. 10 times as much matter in that gas as is in all the stars that we've been used to seeing for hundreds of years. We expected to see the gas. We knew it was there, but we didn't expect to see anything exciting other than being able to measure the temperature and the mass. But we see all this structure in the gas. They all look like this. It's really very, very exciting. So another big discovery, the first time we looked at a cluster. There is a supermassive black hole down in the core of that brightest cluster galaxy, right here. And the black are basically voids in the gas. So we have a supermassive black hole, we have radio jets coming out, and those radio jets are pushing the hot gas out of the way. And so you get a void when you look in the X-rays. If you look in the radio, you actually see emission in that void. And I'll show you another one in a minute. So this supermassive black hole has jets that have caused these voids, and then it's had other jets that caused these voids longer ago. And those voids just keep moving outwards. So this structure gives us a fossil record of all the activity that happened in that central supermassive black hole over the years. We also see these huge swirls, which are called cold fronts, just like cold fronts in our atmosphere on Earth, which are probably a result of two clusters moving quite close to one another, but not being captured by each other, but just the gravitational forces swirl all that material around. So we get shock fronts here, well, cold fronts here as well. The shock fronts are the ones around the voids. So if I look at another one, which is further away, and we can really see all the structure in one go. This one, in this one, the stars and the galaxies are in white. The red is the radio emission, and the blue is the hot gas. So slightly different coloring from the last one. But you can see the supermassive black hole with its bright accretion disk at the center here. Oops. And the radio plasma, the radio emitting plasma, is moving along the magnetic field lines. You can see it also changed direction at some point. If you look carefully, you'll see there's not much X-ray gas around this radio emitting plasma. So this is why we think the plasma is pushing the X-ray gas out of the way. And it's probably heating it up. So we've got an active nucleus. We've got plasma heating up the X-ray gas and making it hotter, while the nucleus is actively accreting material. When it runs out of material to accrete, it will turn off, and the jets will gradually fade away. And this hot gas will gradually cool down. And it will then be able to, some of it will fall into the middle and some of it will form stars. And then when enough has fallen into the middle, the supermassive black hole will once again start accreting. So it will become active again, and then you'll get the jets again. So this forms a cycle, very like a feedback loop. Well, we call it a feedback loop. It's very like the cycle in the thermostat in your house. When the temperature goes down, the thermostat says, hey, it's cold in here, let's turn on the heating. The heating heats up the room. It goes above a certain temperature and the thermostat turns it off. Here we've got a very similar cycle, but what it's controlling is the rate of star formation and the activity and growth of the supermassive black hole. So those two things sort of keep handing the baton to one another as this feedback loop keeps working. So this was not known at all until we started observing these things with Chandra. This particular source has the largest continuous radio jet. It's about 1 million light years from end to end. So it's been going for a long time, that one. We think they usually last about 10 to the 6, so 1 million years or 10 million years at the maximum before they run out of material. Okay, and my final science topic is dark matter. In clusters of galaxies, we still don't have enough matter to keep all those galaxies there. If we add together the mass of the galaxies and the mass of the hot gas, there's still not enough. They'd just escape, wouldn't hold them there. So we know there's about 10 times more matter in a cluster of galaxies than we see in hot gas or in the galaxies themselves. But it's dark, we don't see it, so we call it dark matter. And we don't really know what it is. We have some ideas, but we don't know for sure what it is yet. Now we can visualize where the dark matter is by observing clusters that are interacting with one another. And this is the first one that we looked at that we were able to constrain the dark matter at some level. So on the right-hand side, I have the star field, and also this is 2 clusters of galaxies that are moving through one another. They come together and they move through one another. It's called the bullet cluster because of this shock wave in the red here on the right-hand side. It looks a bit like a bullet being shot through a smoke screen, I suppose. So the white is all the galaxies. The red is the hot gas now. So we're not seeing radioplasma here. We're just seeing hot gas in the red. And there are 2 clumps of hot gas, which were part of the original cluster. There's 2 clumps of galaxies, which are further away from each other than their hot gas. And the blue is now indicating where the dark matter is. And the way we find that out is because when you've got a lot of material, you can actually lens light in a way very similar to an optical lens in your glasses that bends the light. So the gravitational force of the dark matter bends that light. And what happens is that some of these galaxies then look like curves on the sky, and you can measure how much matter, or the mass of that matter that was required to bend those galaxies. It's kind of hard to see that on here, but there are a few that are very long and thin, like that one, for example, is very long and thin. And so from that, we can figure out how much mass that is and where it is, just from looking at the shapes of these galaxies. So what do we learn from this? Well, the hot gas fills all the space, and it comes towards, one lot comes towards the other lot, and each atom that it sees the gas going the other direction. So it slows itself down. So if you think about a smoke ring going through the air, it doesn't go very far. It gets slowed down because the air molecules slow it down. If you think about the galaxies, though, they're more like a bullet going through the air. They're very dense. There's a lot of space between them. They don't tend to see another galaxy or really feel it. Most of them don't. Maybe one or two hit another galaxy or get close, but most of them just keep going and don't notice that they're going through a cluster at all. So they keep going, and the X-ray gas slows down. So you get the separation you're seeing in this picture. But where is the dark matter? The dark matter has moved with the galaxies. So even though the dark matter, we assume, is filling all that space because there's a lot of it, we don't know what the particles are, but they must be filling that space, but they're not seeing one another. So this gives us a constraint on the kinds of particles that make up dark matter. They have to not interact. There's what's called a self-interaction. So there's no drag on the dark matter. And we can limit the particles that are candidates for dark matter as a result of knowing that the interaction cross-section is less than a certain amount from these measurements. This is an animation made by our EPO people that shows the dark matter and the gas going through. So you can see what my hands were trying to explain to you. It comes down to the red gas in the middle, and the dark matter keeps going. So that's how we got this structure. Okay. I just want to show you this one. This is also a cluster of galaxies that's interacting, because you can get all kinds of shapes in these. This is, I think, the last science picture I'm going to show. This one was christened by our outreach people as the Starship Enterprise for obvious reasons when you look at the structure. The white, again, are galaxies. The purple is the hot X-ray gas. And the clusters are coming from the top and the bottom and interacting with one another. The blue is the radio emission. And we have a number of active galaxies in this cluster and a lot of different structures here. So we have short jets labeled here. These are galaxies that are moving through plasma. They have their two jets going out in two directions, but they get bent back by the interaction with the plasma. And you end up with what's called it could be a head-tail source or just a single-tail source, because the two jets almost come together. The same thing is happening where it's called the star drive section on the left here. It's a little bit wider, but again, we've got the jets streaming back behind the source as it moves, as the active galaxy moves through the material. We also have a couple of what are called radio phoenixes. So after a radio source has died and the supermassive black hole has stopped being active, there's a lot of plasma that's just cooling down, sitting there, and you don't see it until something lights it up. So if you've got this plasma sitting there and then another active galaxy comes by, for example, it can light up that plasma, and you get what we call a radio phoenix. It's not really attached to the supermassive black hole. The supermassive black hole just came near enough to heat it up again. So that's what creates these two structures, and also the structure at the bottom. So it's just a lot of fun, and it looks like the Starship Enterprise because of the sources section up here and the star drive section down below. So this is one of our press releases. Basically, re-energizing the plasma in these cases and bending the jets in the other cases. Okay. So I just want to finish up with some pictures of our astronauts. I mentioned that we still are in touch with them. They come back to our science conferences, which we've had quite frequently, to begin with every 2 years, and now we do them every 5 years. And this was the picture of the 2014 one, which is right after this is a picture of them up on the shuttle with what we would call a banner in the States, but it's a flag behind, which has Chandra X-ray Center written on it. They took that up in the shuttle, and there's a picture of them there. You can see their hairs all in the air because there's no gravity up there. They brought that flag down, and we have it hanging in our control room, which is now in Burlington, Massachusetts. So that was how young they looked at that time. This was in 2014 for our 15 years of Chandra science. This is 4 of them. Probably should have said who was who in the last one, but I'll do it here. So this is Eileen Collins with the white trousers here, she was the commander. On the right is Katie Coleman, who was our Chandra mission specialist. So she took the movie I showed at the beginning. This is an ESA astronaut called Michel Tognini. And then on the left is Steve Hawley, who actually has been up on several shuttle missions that are related to astronomy. He's been on at least 2 of the Hubble missions, and of course this one as well. He was an astronomer before he became an astronaut, and now he's an astronomer again now. So he's seen both worlds. The pictures behind are just some of our pictures, as I'm sure you realize you might even recognize. No, maybe not. Oh, this is the crab, actually, above Eileen's head. That's the crab. And above Steve's head is the Cassiopeia. And then, just to prove I was there, that's me with the astronauts. And then we had them come back again, or they came back again, 3 of them, now Eileen and Steve and Katie, in 2019 for our 20 years at Chandra. These are both conferences that took place in the Boston area. And the other 2 weren't able to come. So they actually showed us footage of the launch, which none of us had ever seen before, and a lot of the stuff that went on that they didn't know about at the time. I mentioned that there was a problem with one of the engines, but there were actually several other major problems that went wrong that they had getting Columbia up into orbit that day. And it was rather strange because 20 years later, we're sitting listening to this footage, and at the end of it, you go, wow, it finally got up there. And you're thinking, well, yes, of course it did. We've been using it for 20 years, but you almost felt really relieved that it got up there with all the problems that they had. Apparently, it's incredibly unusual. But I do know that they were looking for places to land it pretty much right after it took off because one of the computers went down. But there is a backup. It fell over to the backup, which picked up, and they were able to carry on. And it's questionable whether they could have got down safely at that point. So anyway, all's well that ends well, and we're still observing with Chandra. And my last slide is just some of those images. There's a crab again on the left. And this is NGC 6240 with a double quasar. And there's our website address here, in case you might want to look at some of our beautiful images. I make these talks just by taking the ones that are used for the press. And they're just a really good team that make these images and turn what we don't look at them in color when we do our data analysis. We just measure it, measure the energy, look at the spectrum. We don't make pretty pictures like this. But this is a really good way of illustrating these sources in a way that anyone from the public can appreciate. So thank you, and I'd be very happy to answer questions. So I had to bring this up to see the people. Do I have to do anything here?
No, we can. Well, it depends. If you think you might want to go back to your slides, we better keep your slideshow up.
Yeah. Okay.
But, right. So Charles is. That's the speaking.
Yes.
So we'll take questions now. If you're on Zoom, then we'll monitor the chat channel and so please just type your question in there. If you're in the room, raise your hand. Okay, Peter.
You showed jets that they bent. What would make them bend? There didn't seem to be anything there.
No, just. But,
can you repeat the question?
Yes, sorry. Thank you for reminding me. Yeah, so the question was, what makes the jets bend? You've got this relativistic outflow. It's actually going extremely fast. There's plasma streaming along the magnetic fields, but it must hit cold matter that we can't see in any way. If you remember looking at the star forming region, there were just dark areas and light areas. The dark areas were just cold material that blocks the view of everything else. So we've got dense matter, and the plasma is coming along, and it hits the dense matter and gets deflected. But yeah, you can't see the dark matter, at least not in these wavelengths.
Okay.
All the way at the back. Yeah, you.
inquiry to
Great.
see.
Great.
So to focus on something that's quite sort of sensitive to the whole thing that came up in my mind. These combining all sorts of beautiful life experiences.
Yeah.
Give you an idea of you can then conclude that you can supervise which actually matter of gas.
Yeah.
So I think what the very first slide that you showed, in that you talked about the colors representing elements.
Yes.
So that galaxies that is other than sun are quite advanced because matter has formed from the galaxies. And quite confident in that.
Yeah.
So, my question reference to that aspect is that engagement the iron that was showing and all of the development, are they engagement or
Yeah, okay, they're gaseous, but I'll repeat the question. So the question was about the supernova remnant, Cassiopeia A, that I showed fairly early on. I was going to go back to it, but it's just too far. And about the elements that we see, because we have the spectrum as well as the image, we can see the emission lines of certain elements. We know what they are, we can see where they are. And so the question was, is that in gaseous form? And the answer is yes. Because it's very, very hot, so it couldn't be in solid form in any way. And so the lines are a result of an atom has a nucleus and electrons around it, and they get excited when there's a lot of material around. The electrons jump up and down, and then they fall down again. So you get emission lines that are characteristic of those elements, that only those elements would give. So yes, they're in gaseous form. And yes, they are pretty advanced. That's one thing I forgot to say, actually, that the heavy elements, what we call heavy elements, which is anything heavier than helium and hydrogen, are created in the centers of stars by fusion. So I mentioned the fusion, but I didn't take it any further. And then when the supernova goes off, all those heavy elements go out into space. It just keeps expanding. And they can then form the next generation of stars. And so those stars are formed from fairly what we call enriched material. So there are heavy elements already there. Now, we have enriched material in our bodies and on Earth. That's what we're all made of. We're not made of hydrogen and helium. So our Earth must have come through as the next generation of stars. And the atoms in our body, in our bodies, were formed in the middle of a star, which then went supernova. So we're actually made of stardust.
Plasma, because when you're showing images of the color spectrum of
a few questions.
Yeah, maybe I can speak to you after.
with matter and gas. The plasma, how can it reduce from the different colors that we see when the plasma, which is a very basic, form of energy, like the energy level, and these more sort of advanced matter particles.
Okay, so how do we distinguish the particles that we're seeing? Is because we see the emission line at a certain wavelength, and we understand the atoms of different types of elements. We then know that at a line in the X-ray at this wavelength, or energy is what we measure in the X-ray, comes from that atom.
Okay.
So it's characteristic of that atom.
We take one more.
Okay.
Then we'll go to the chat channel.
Thank you.
Early on, you actually showing a bit like clusters of early stars.
Yes.
Actually, do you feel like you have these sort of time resolutions so you see them there? And actually do those variations to match sort of other way as well, so it's visible.
Yes.
actually do that chart from like different about.
Yeah, it depends on the source. But yeah, so the question was that when we got stars forming, and actually it's true of many different types of celestial sources, sometimes they vary, and these violent places like stars that are forming do tend to vary because they're very violent and lots going on. Do they vary the same way in different wavelengths? So sometimes they do and sometimes they don't, is the answer. And sometimes they do in a related way. And you can actually learn about the structure of the star by looking at, say, the X-rays vary first and the optical varies later. It probably means that the star in the core has created some kind of energy that gives you the X-rays. The X-ray emitting material is the hottest, so it's closest to that change. And then further out, you then have the optical cooler material that gets hit by whatever shock wave, and that varies. So you can actually measure the structure of an object when that kind of thing happens. It's mostly used to measure the structure of quasars, active nuclei, because you see they emit different emission lines, and also the X-ray emission, they vary at different times. So you think supermassive black hole has sudden burst of energy comes out, heats up the X-ray material. You see that luminosity, the amount of light you're getting, increase first, and then it gets a little bit further out. There's the accretion disk, and you start seeing the emission lines and the continuum from the accretion disk vary. You can actually measure the size of something that you can't resolve spatially by looking at that timing. It's really very powerful. Yeah, good question.
It's Charles now.
Yeah, one question, double one really from Fergus, which is how long does Chandra have left? Any plans for replacement?
Yes, very good question. We hope it has a long time left. It is aging. The temperatures are going up, so we have to be. Sorry, should I repeat? I should repeat the question.
I think so, yes.
Okay, sorry, I'll repeat the question, which was how long does China have left to work, and is there anything that will replace it? So we hope it'll go for quite a lot longer, but it is aging. We know that the thermal insulation is degrading and the temperatures of everything on the satellite are gradually increasing. And what that means is we have to very carefully plan our mission so that each component on the satellite doesn't get too hot. And they get hot when they're pointing towards the sun. So we're doing shorter and shorter observations. We have to look over here, and then we have to look over here, so we can cool off the thing that got hot when we were looking over there. But when we're doing that, another component's getting hot, so then we have to turn back. So it's very complicated to operate it now. But at the moment, we're still operating at the same, what we call observing efficiency, which is 70% of real time, 70% of wall clock time we're observing, which is the maximum we can, because when we're in the radiation zones, for about 30% of the time we can't observe. So at the moment, we're still managing to do just as much science. That won't go on forever.
Is fuel a limiting resource?
Fuel is not a limiting resource. So yeah, we'll keep going as long as we can still observe. And we'll just gradually get less efficient. In terms of replacement, the answer is no at the moment. There's no planned replacement, and there's nothing else in the X-rays that has the spatial resolution Chandra has. There's an ESA mission called Athena, which is planned, but that resolution for that will be back at a few arc seconds. It'll have a much bigger mirror, so we'll be able to look further from that point of view. There was a mission called LINX that was proposed to the US-based NASA Decadal Survey as one of the big missions, and it's still in the running, but it would not fly, assuming it keeps going in terms of being funded. It would not fly until probably 2050, so most of us would not be here any longer. And there's a smaller one that uses the same mirror technology, because now we can't use the same mirror technology. These are very big, heavy mirrors, and to get a bigger one, we just wouldn't be able to send it up in a rocket. So we've got to do new mirror technology that is with very thin glass. It's sort of glass base and then covered, and you put lots and lots and lots of them. There's lots of space in between the mirrors of Chandra, so you can fill that with more, and they will be lightweight. So there's what's called what they're calling it, probe class mission, which is a lot smaller in terms of cost than a great observatory. That is being designed and hoping to get approved for funding, and that would be able to go probably within 10 years. And it would do the imaging, but it wouldn't do all the other stuff that LINX would do. It wouldn't get high resolution spectroscopy. It wouldn't get the calorimeter, which does the spectroscopy and imaging combined at much higher resolution than the detectors on Chandra. So hopefully that will go as well, but we have to wait and see. But as soon at the moment, when Chandra dies, there's nothing left that will be able to resolve these sources in the X-rays.
Have you got anything else there? No, that's it. That's it. Yep. Okay. Thank you.
Have you looked at the hotspots in the radio jets and do spectroscopy?
In the X-rays, no, not to see lines in the. But it's continuum emission, really. Synchrotron emission. It should be continuum.
The heavy elements up to uranium. We've seen them in the relativistic region. So gammas of 3 or 4.
With what?
The cosmic ray satellite.
Oh, the cosmic rays. Yes. Yes. Okay. Yeah, we actually see the structures that might be generating cosmic rays in these in the supernova remnants, but that's spatially resolving a structure. That is part of the synchrotron emission. So the purple stuff, there are lines that are separated, at the right spacing to be a place where cosmic rays are generated. But we haven't sent any emission lines from that, as far as I know. Not from that plasma.
Look at the radius.
Could what? James?
The James space.
Yes, probably.
Spectroscopy.
Yeah, it is. Yes, good. And it's got very high spatial resolution. I don't know if it has done that yet.
There's a question at the back.
Yeah. A quick question. You've mentioned that you're not worried about running out of fuel in the mission, but if you're looking at targets for hours at a time or days at a time, given the relatively fast orbit wide that the telescope is on, how does the telescope keep pointing at the same target for such a long time without fuel?
Yeah, we do have fuel, but we have plenty of it. It would take hundreds of years to run out of fuel. So that's not our limiting factor.
So 20 years worth of exploration, that's not.
It's not used up a large fraction of our fuel. We do monitor it and we see it come down, but there's plenty more left. So that's sorry.
Is that a common? Often we hear that space observatories will be limited even.
Yeah, I forgot to repeat the question, didn't I? Sorry. I'm talking about, is fuel a limiting factor for Chandra, and it is not, because there's plenty of it. We had to have a lot of fuel to get from the shuttle orbit out to this high orbit, and we didn't use it all. So there's still plenty there. And yeah, as you say, you are using it all the time, but there's plenty of it. And similarly, the orbit won't decay in any short time frame either. So the limiting factor is funding and just the fact that everything's heating up and eventually something will fail as a result of that. Yeah, go on, Bob.
Your answer there prompted me to ask the question, could you not have put it in an orbit which was a little bit above the radiating belts and gave it more observing time, or was that a fuel?
That would have taken a lot more fuel.
Right,
yeah. To raise both the perigee and the apogee, yeah. It would have been, wouldn't have been able to get it up there, it would have been too heavy. Originally, it was supposed to be in the shuttle orbit. Oh, I forgot to repeat your question again. Originally, it was supposed to be in the shuttle orbit. At some point, NASA decided to save money by, I don't know why that saved money, but by sending us further up. It means that we can observe the same source, or we could, for the thermal problems for a long time, which is quite useful when you've got variable sources, but there are a lot of those in the X-rays. But yeah. Yes.
Yeah, when I was involved with this stuff 40 odd years ago, originally, I was doing cosmic ray stuff. We had X-ray telescope payloads on the same spacecraft. and they had a very limited lifetime. They had very thin plastic windows, gas detection, and they leaked.
Mm.
And they had to, and when the gas supply had gone, it was gone. That was it. What sort of detectors do you have?
Do we have? Yeah. Okay. So the question is, how do the X-ray detectors on Chandra compare with ones 30, 40 years ago that were used that didn't last very long because they leaked gas? On Chandra, the primary detector is called the ACES. It's a CCD detector. There are actually two arrays, and they're special CCDs that have been, I don't know what you have to do to them, but they actually detect X-rays. So that's what's used most of the time. We do have a microchannel plate, so that would have gas in it. So I guess they've got better seals these days. The high resolution camera is a microchannel plate array. But actually, we've just had a problem with that. It isn't working right now. It's failed. Both sides of it have failed, and we're trying to get to a point where we can observe short observations with it, because we can sometimes get it to last about 10 hours, and we've still got observations to make. But at the moment, I don't think we're using it at all. They're taking tests, but they haven't done any observations with it for a few months now. But yeah, it has worked for a long time, 23 years, worked very well. It doesn't give us the energy resolution that the CCDs do, but it has a little bit higher spatial resolution, and it has higher timing resolution. It's very good for observing variable sources.
What was the predicted lifetime? Is it exceeded that?
Oh yeah, the predicted lifetime. The question of what was the predicted lifetime was 5 years maximum for the mission. So of course everyone designs things to last longer than that, and we've been lucky that everything's lasted as long as it has. Same happened with Hubble. I mean, that's still going at almost 30 years now. So.
Right, let's think about one more question. Did you have one?
Yeah, it was only given the chance once again to like we like design challenge on it. What is the one thing that you was showing? So what I have to use it for 20 years, do you think would have been better?
So if I understood your question, it was what might we have done differently having used it for 23 years? You know, what could have made it even better? I mean, well, obviously, detectors we can make on the ground now are more advanced, but we couldn't make them then, so not that. However, you may have noticed that there were 4 mirrors and they weren't equally spaced in radius. There used to be 6 mirrors, and there used to be another detector. I mean, this was in the design phase before it was built. There used to be another detector, which was a calorimeter, which is a heat-based detector, which can do, I mentioned it earlier, can do imaging and high spatial resolution imaging and high resolution spectroscopy all at once. With the CCDs, we do low resolution spectroscopy with that imaging. So you only see the strongest lines and they look fairly broad. The calorimeter was supposed to go up on Chandra, but at some point NASA cut the funding, and they had to cut, this is before I was working on it, they had to cut 2 of the mirrors. This is probably also when it went into a high orbit, and we had to cut the calorimeter. And at the time we were promised that calorimeter would go on another mission. It was called AXAT-S, but that didn't fly. And the calorimeter then flew on a Japanese-US mission, small mission, which was probably about 7 or 8 years ago now. And some of you, if you follow these, might remember it. And I forgot what it was called. It went up, and within a few days, it just went spiraling out of control, and it broke apart as a result. But we're getting a replacement. A new one was built, and it should go up next year, called Prism. So if there was anything, long story, but if there was anything I would improve, it would be to keep that calorimeter on Chandra. But we weren't able to do that.
Thank you. So this evening we've been taken on a tour right through the universe, from the planetary aurora right up to the larger scale structures of galaxy clusters. And absolutely amazing to hear about a space observatory that has got such high resolution and has lasted so long. So this has been a really interesting talk, and I'd like you to thank the lecturer again, please.
Can I make one more point, actually? That we've lasted 23 years without any servicing. The hub is still going, but they've had quite a few servicing missions. So it's even more of a feat to be able to keep going without any servicing.
Detect a bit of smoke.
Bar up, yeah, just a little bit. We have to beat them somewhere, right? But there are paths we observe them a lot. So thank you for coming. It's been a real pleasure. Oh, you're welcome. I'll give you questions.
Yeah, because it's fascinating that the advance in technology has allowed us to actually observe the formation of galaxies.
Mm-hmm. Yeah, it is.
Because I mean, you know, I'm familiar with.
Yeah.
But I came across this whole concept of quantum gravity by accident here in this country, because these companies